The U.S. Space Agency NASA documented one of the most disconcerting astronomical events in recent history in October 2025. The interstellar comet 3I/Atlas inexplicably interrupted its orbital trajectory near Mars, remaining stationary for days. Located approximately 27 million kilometers from the red planet, this object followed a hyperbolic trajectory, characteristic of rapidly passing celestial bodies that, in theory, should not experience significant interruptions. This event fundamentally defies the known laws of orbital physics and transformed 3I/Atlas into a natural laboratory of urgent need. The massive data collection by ground-based telescopes and Martian probes has sparked a global hunt for scientific explanations that could decipher this atypical behavior, demanding an immediate reevaluation of our most robust cosmic models. 3I/Atlas was already an object of immense importance even before its immobilization, being the third interstellar object identified to pass through our solar system. Its origin is estimated to date back an impressive 10 billion years, predicting the very formation of our Sun, making it a primordial time capsule of distant star systems. Its nucleus is relatively small, ranging from 320 meters to 5.6 kilometers in diameter, surrounded by a dense cloud of gas and dust. Its trajectory, upon detection, was typically hyperbolic and unprecedentedly slow, and after resuming its movement, the comet continued toward its closest point to the Sun, perihelion, scheduled for October 29, 2025. The chemical composition of this stellar visitor distinguishes it from virtually all comets native to the solar system. Spectroscopic analysis revealed a high concentration of carbon dioxide, CO2, in its coma and, simultaneously, a remarkably low presence of water ice. This signature suggests that 3I/Atlas formed in the deep, dark regions of a distant star system, perhaps a volatile-rich molecular nebula, where the temperature was low enough to preserve vast quantities of frozen CO2. This characteristic not only provides valuable information about the environment of its parent system, but also complicates understanding its dynamics, since the absence of vigorous water sublimation affects how it interacts with solar radiation. The period during which 3I/Atlas remained nearly static relative to the background stars, the anomaly itself, strongly contradicts current celestial orbital models, which relies strictly on gravitational calculations. NASA quickly ruled out any possibility of instrumental error, validating the accuracy of the records made by multiple independent platforms. This confirmation makes it imperative to postulate that non-gravitational forces, possibly unprecedented on such a scale, acted as a powerful cosmic brake on its trajectory. The event forces the scientific community to rethink the complexity of the interplanetary and interstellar environment, requiring substantial revisions to the orbital simulation software used globally. One of the leading hypotheses for the comet's temporary stasis lies in the comet's interaction with cosmic electromagnetic forces. Spectroscopic data, still undergoing detailed analysis, have indicated the existence of subtle vibrations in the comet's nucleus during the stasis. Theorists suggest that 3I/Atlas may have momentarily interacted with an intense magnetic field from unknown sources, or with a dense, localized flow of interstellar plasma. The detection of metallic grains and possibly magnetic iron on the comet's surface adds weight to this theory, as these elements could have reacted to the surrounding electromagnetic field, creating a drag effect or temporary stabilization that neutralizes its gravitational pull. Another line of research points to intrinsic comet stabilization mechanisms. This theory involves a manifestation of symmetrical microplumes of gas, a rare phenomenon in comets, which would have acted analogously to tiny equilibrium thrusters. If the comet had expelled gas perfectly evenly in opposite directions, perhaps due to symmetrical faults or fissures in the nucleus. It could have neutralized its own velocity, remaining in a state of momentary near stasis. The possibility of these plumes suggests that 3I/Atlas has a significantly more complex, homogeneous, or resilient internal structure than that of comets created in the solar system, indicating that internal dynamics are key to explaining the mystery. The event's proximity to the orbit of Mars proved to be a fortunate scientific coincidence. The probes, rovers, and orbiters operating in the Martian region were immediately redeployed to monitor 3I/Atlas, ensuring unparalleled data capture. The event provided a panorama of extremely high-resolution images and spectroscopic records, many of which are still being processed, offering an unprecedented view of an interstellar body in action. This data acquisition under optimized conditions has transformed the comet into a unique study object for understanding rare cosmic phenomena and directly contributes to the research of stellar systems formed eons ago, long before Earth. The main impact of this episode is the need for an immediate update to celestial models. The behavior of 3I/Atlas irrefutably demonstrates that non-gravitational interactions are critical variables that must be included and considered in predictive calculations. Refining simulation software will be vital to improving the trajectory prediction of all transiting objects and reinforces the imperative need to invest in investigating unknown forces and plasma operating in the vast expanses of space. The comet's pause serves as a powerful reminder of our limited understanding of the deeper mechanics that govern the universe and highlights the urgency of maintaining continuous observations of interstellar objects, given their unpredictable nature. After its dramatic pause, 3I/Atlas accelerated. Resuming its course toward its closest point to the Sun, detailed observations will continue intensively, focusing especially on gas emissions and brightness variations as the comet reacts to the increasing solar heat. Its outward journey from our system includes a pass through the orbit of Venus in November 2025, followed by a close flyby of Jupiter in March 2026, before continuing its final journey back into interstellar space. 3I/Atlas, with its brief and enigmatic stopover, has cemented itself as a key cosmic object, offering new insights into planetary formation and, crucially, challenging our fundamental understanding of how matter moves through the cosmos.